All right, our last speaker of the session is Mr. Patrick TomHon from North Carolina State University. As you may know, he's not just a graduate student and a researcher, but he's also one of our co-organizers. And honestly, if it weren't for him and his technical expertise, I don't think I would believe we would even be able to pull this off. You wouldn't believe how many times I ask him stupid questions just to get where I am right now. And yet somehow he's going to give this talk. And I hear, just to add to the degree of difficulty, he's planning a live demonstration. So we're going to see how that goes. Take it away, Patrick.
Thank you. Can you hear me okay? And can you see the presentation?
Yes.
Okay, great. So today I'm going to be presenting some of the research that we've been working on here at North Carolina State University. We call this system the PHIP-MARS system, which is a parahydrogen-induced polarization membrane reactor system. This is something we put together in our group, in the TICE hyperpolarization group, with close collaboration with some of our colleagues over at the Department of Chemical and Biomedical Engineering just across the street. And so just a short outline of what I'm going to be talking about. First, I'll review some of the existing PHIP and SABRE methods. And then I'll go into a detailed discussion of our system characteristics, methods, and design, and kind of the development process behind this. This is still work in progress right now. We're still exploring a lot of the applications of what we can do with this PHIP-MARS system. And then I'll talk about one of the, a detailed discussion of one of the specific applications, which is a continuous RASER, SABRE RASER at 1.1 Tesla in a Spinsolve, where there's no signal decay. And as we continuously refresh the polarization with our MARS reactor. And then, as you notice, I'm in the lab right now. And as Boyd mentioned, I'll be doing a live demo of the PHIP-MARS system that's currently running in the background right now, including showing acquisition of a single mode RASER on Pyrazine. So first, again, I'll start with an existing review of instrumentation. I'll discuss some of our recently published work and the methods that we use on a day-to-day basis in our lab right now. And then I'll discuss how the PHIP-MARS system addresses some of the shortcomings of existing PHIP instrumentation. So as we all know, and as has been shown throughout this entire conference, there's a lot of really great methods for conducting PHIP and SABRE experiments. Some of these traditional methods are the shake and drop methods and the bubble and transfer. And what's shown on this slide is just a small snippet of the literature that exists around a lot of these. But I tried to capture really the breadth of methods that are applied for PHIP and SABRE experiments. And of course, we have mechanical shuttling shown by Chu et al. In 2012, but then also there's been some great work published out of the groups in Novosibirsk, showing some very fast and reproducible mechanical shuttling techniques for field cycling. And of course, the recent work that we published as well with pneumatic shuttling, very simple shuttle that also enables reproducible and fast acquisition of SABRE experiments. And then all the continuous automated methods that also exist. Really, a lot of that in this conference has been pretty amazing. With bubbling reservoirs as shown in the groups in Oulu and York in the past, and then also the membrane-driven continuous automated methods that one of them was pioneered by one of my fellow group members, Soren Lempool at Aachen in his PhD work, and then also really some nice work was also presented from Southampton, where they're doing really cool microscale fluidics. Well, the volumes we deal with are a little bit larger than that. So just to highlight some of our recent work, I've put together this pneumatic shuttle that is very simple. All it uses is nitrogen and vacuum in a polycarbonate tube to move the sample up and down. It allows for very reproducible spectra. And one example of this is the 2D characterization of binding modes and catalytic isomers in a SABRE process. And here we show how hydride peaks of a dual pyridine and acetonitrile SABRE sample can be easily identified. Each species can be easily identified using 15N and 1H inverse HSQC spectra acquired using the shuttling system. However, kind of the question that we've been asking ourselves is, like, how do we move forward with PHIP and SABRE, and what are the demands of a generalized PHIP that can operate at any magnetic field and gives very high levels of polarization. And so what I put on this slide is kind of a snapshot of what we think are the most critical demands for this general PHIP-SABRE setup that I'm going to dig into, and what we think we've addressed, which is high functionality for both SABRE and PHIP experiments. And when I say PHIP, I'm referring to generally like hydrogenated PHIP experiments. Obviously, high hydrogen dissolution is a very important factor in increasing the functionality. Automated and extending operating periods are also very important. And this includes minimizing sample loss over those extended operating periods. And then a compact modular design, something that is easily portable, can fit in a small location, can go next to a benchtop spectrometer or a high field spectrometer or an MRI. And then also the final one is rapid production of hyperpolarized media. And this includes as well preparation of samples on a milliliter scale with the eye toward eventual in vivo applications like was just presented in the previous presentation. So we think that the PHIP-MARS system addresses a number of these aspects and demands that I just talked about. Really what we've done is use a polymer that has a fluoropolymer that has a very high gas permeability. So instead of using PTFE has been used in the literature a lot, which has a gas permeability of 980 centibar. The AF Teflon 2400 tubing that we're using has a permeability of 220,000 centibar, so over or a little bit under 1,000 times the gas permeability with regards to hydrogen. And our design is very compact. So the reactor shown on this slide here is 10 centimeters, about 10 centimeters long, 2 centimeters in diameter, so it can easily fit within any solenoid or any shielding. We're actually getting smaller shielding so we can decrease the size of our system overall. And as well, this design can be easily parallelized or extended just using longer fluoropolymer tubing lengths. And it enables continuous production of hyperpolarized media for over 7 hours per 10 milliliters. Our typical operating values when I do experiments with this system are 8 milliliters, and I'll operate for up to 6 to 7 hours with that. Pushing the volume higher gives us even longer operating times. We see very low levels of evaporation, especially high pressures. It's only about less than 1 milliliter of evaporation every 5 hours. And on the right here is just an example spectrum of some early results that we acquired on pyridine SABRE with this system, with the PHIP-MARS system. And here we achieved, with 50% parahydrogen, polarization of 1.18 fold at 1.1 Tesla. And this is all in flow. So none of these are stop flow experiments. This is all done in continuous flow acquisition. So now I'll talk a little bit more about the details of how the PHIP-MARS system works, some specifics about the instrumentation, and each of the individual components that we're using. So here's just a depiction of the configuration that we're currently using that I have operating next to me right now. And in the next couple of slides, I'll go through and walk through these components and explain the fluid path. For pumping, we're using a high pressure single piston HPLC pump from Teledyne. This enables us to tolerate very high back pressures when we pressurize with high levels of parahydrogen. For detection, we're using a 43 megahertz Spinsolve, so 1.1 Tesla. And this includes a flow probe through the Spinsolve that we're using from Magnetization that runs the length of the magnet bore. And so we pump the solution up from the bottom, as shown in the diagram here, from the bottom of the flow probe up to the top of the flow probe, and that's how it cycles through. And then finally, the most critical component, of course, is the reactor itself. And this reactor, as I described, is about 10 centimeters in length. So we put it on a 3D printed scaffold, and we wrap the reactor tubing around that scaffold to decrease the size and increase how compact the design is. And this can be extended, of course, and even made more compact through tighter coils of the tubing. Additionally, we use a hand wrap solenoid that can ramp comfortably from Earth's magnetic field up to 15 millitesla. And this reactor fits very comfortably inside this system. And we'll be getting a shield for this as well. That's around the size of that solenoid. So a little bit about how this reactor actually works is it's a tube-in-tube system where the AF Teflon 2400 tubing is inside an outer fluoropolymer tubing. So the gas flows on the outside and the liquid flows through the inside of that gas permeable tubing. And on the bottom left here is a diagram of the saturation profile over a length of the tube-in-tube system. And this is simulation work. I just want to mention quickly, this is simulation work done by Klaus Jensen at MIT. He's a collaborator actually of our collaborators across the street in chemical and biomedical engineering. And then on the right here is simulations of the saturation profile inside the tubing, retention time of the reactor. So on the left here is 2 seconds of retention time, and the right is 10 seconds of retention time. So you can see very quickly the solution is saturated with gas once it enters this tube-in-tube system. And just a short description about the dimensionality of the current system. All the tubing, the housing, the wiring, cabling, everything fits inside casing that is actually a computer casing, slightly less than 2 by 2 by 2 feet, so just about a cube. And here's a small plot about the retention and transfer times in this PHIP-MARS system at variable flow rate. So here, orange is the transfer time, the retention time in the sensitive volume of the Spinsolve. Purple is the transfer time from the end of the tube-in-tube reactor to the sensitive volume of the flow cell. And red is the retention time in the tube-in-tube reactor. So you can see our transfer times are actually, our retention times are very high, which is great, but our transfer times are actually a little bit long at this point, and this is something we're working on to and I'll talk about a little bit more in a few slides. So one of the main issues in continuously cycling solution, especially in laminar flow, is displacement of orthohydrogen from solution to allow large volumes of fresh parahydrogen to enter. So we propose 2 possible solutions to solving this problem. One is depressurization of the liquid phase after acquisition to draw large H2 volumes out, allowing large H2 volumes back in. And the second is a degassing stage at about the same pressure as the primary stage, using another tube-in-tube reactor with inert gas flow instead of parahydrogen flow, relying on partial pressure to drive the H2 out. And it's just shown here where we have that secondary phase, degassing displacement phase initiated. So the first method I'll talk about is this back pressure regulator method. So here's a diagram showing a first solution where we inserted a fluid back pressure regulator shown here on the right. This is an instrument that we purchased from Bronkhorst. And the BPR allows for a high pressure input and then digitally controls the output through an incremental valve to give a depressurized line on the other side of the device. We're also using a similar device in our gas phase of our tube-in-tube reactor to control pressure on the reactor here. In this configuration, we actually saw pretty poor levels of enhancement, although there was a very nice flow dependence still. Our hypothesis of why this is that this low observed polarization is due to disruption in the activity of the catalyst as we flush large volumes of hydrogen out of the solution. And this is the secondary configuration that we have. And so this here is the secondary reactor, and this is the slide that I showed originally, because this is the configuration we're using now. And with this system, we've been able to achieve much higher levels of polarization, almost 10-fold higher than the other depressurization configuration with this secondary reactor. And although this is still kind of a low level of polarization, we're losing a lot of polarization to relaxation effects, specifically because the T1 of pyrazine at 1.1 Tesla is very short. It's only 5.8 seconds. It's even shorter than pyridine, actually. And we estimate that we're losing at least two T1s in this transfer process when the transfer from the reactor to the probe is 28.8 seconds. It's probably actually more than those two T1s. We'd like to move to higher flow rates, but the flow rate is restricted by the line broadening in the sense of volume. And we're working on solutions to shorten the transfer time by manufacturing a new flow cell or running a smaller capillary into the flow cell. And we're really excited to extend this work beyond proton enhancement and proton polarization with SABRE to long-lived states and heteronuclei, such as the SABRE singlet state on pyruvate, because we think with those systems we'll be able to demonstrate really very high levels of polarization. So now I'll move on to the application that we're focused on, and this application is the continuous SABRE RASER. So just quickly, a RASER is an analog to a laser with spontaneous emission of radiation due to population inversion. And this population inversion is generated by SABRE hyperpolarization, and the feedback that gives coherence of the population inversion is from the resonator that is the NMR circuit. And here, this is just a demonstration of using the pneumatic shuttling that I showed to get a single RASER burst in a high field breakthrough magnet with no pulse applied. And our shuttling time is roughly 750 milliseconds from the solenoid at 65 Gauss into the probe. So we're able to observe a single burst just with a very high level of polarization. And RASER effects have also been shown very nicely in some recently published work from Baptiste Joland and Andrei Prevditsev on the left here. However, this is still limited in some respects. On the left, bubbling is turned off before the acquisition to enable RASER activity because of inhomogeneities introduced by the bubbling. And so the polarization source is limited, so the RASER does die off. On the right, they actually induce a continuous RASER with constantly bubbling, but the bubbling is maintained throughout the experiment, so it induces these inhomogeneities that destabilize the RASER and significantly broaden the line. So with continuous flow, we don't need bubbling, and we will expect a stable RASER with our system. And that's what I'll show in the coming slides. So the buildup of polarization at this in our system is demonstrated on this plot. So at 0 seconds here, I open the parahydrogen valve with the gas flowing at 40 mLn per minute, and the pressure is linearly ramped from 0 to 90 psi over the course of this graph. There's a very fast buildup. It takes about 460 seconds to linearly ramp the pressure. That's just due to flow rate. This can be ramped faster if necessary. But then we see this jump at around 6 minutes, and this jump actually corresponds to the beginning of RASER effect. So at 300 seconds, there's an extended T1. There's still, an extended T2. There's an extended FID that we observe in the Pyrazine signal. But we don't see the significant RASER effects until we cross the threshold at around 350 seconds. So by 432 seconds, 565 seconds after turning on the parahydrogen, we see significant raising effects. And similar RASER buildup effects have been observed on pyrazine and acetonitrile in the Apples group at RWH Aachen with a really seminal paper in Nature Physics. So our pyrazine RASER at 1.1 Tesla enables us to acquire for really as long as we want. There are some limitations that I'll address shortly. And here we're just showing a RASER that's acquired with a minimal initialization pulse that just opens the receiver. This is just a 3.3 degree pulse. And the signal observed here is the transverse magnetization from MT shown on the diagram on the left here. This is adapted from that Nature Physics paper. So we're able to Fourier transform a slice of the spectrum to observe this sharpened pyrazine peak. The shim value that we get is actually normally very high due to the fact that we're shimming in flow. So this is acquired while it's shimming at 2 milliliters per minute. But we observe narrowing of the peak, of course, due to the RASER effect. So the full width at half max for this is 0.49 hertz. And there's a very clear dependence on flow of the RASER. As we move higher above threshold, our peak intensity is increased. A similar line width for all of these peaks due to flow artifacts, but we would expect a significant difference when we Fourier transform the whole spectrum instead of a single slice. So here's a plot of the transverse magnetization versus the flow rate. Plot is the inverse, the time from the reactor to the probe. And parameters that impact this transverse magnetization include relaxation, obviously, with lower flow rates, residence time in sensitive volume, and also residence time in the reactor, the amount of time that polarization is actually building up. At 2 milliliters per minute, we observe a maximum in our transverse magnetization, which decreases for the most part to 3.5 milliliters per minute, where we observe no RASER effects then above 4.5 milliliters per minute. However, at 4 milliliters per minute, we have a compounding of nonlinear effects that we're still working to understand. This is probably due to a minimization of relaxation, but also fast repression of highly polarized material into the coil. Lastly, before the demo, I'd like to show a fun application of this Spinsolve RASER. The maximum of our acquisition time is actually around 2.5 minutes with a long dwell time of 1200 microseconds, and this sacrifices resolution a bit. We're actually limited here by the RAM of the Spinsolve. The Spinsolve limits the number of points that can be collected, so we're going to have to work to try and address that in the future. But this allows us to, by Fourier transforming slices of this, as I showed previously, we can acquire a linear fit of the drift of the Spinsolve and observe the temperature drift over time. We calculate that to be roughly 0.7 hertz per second. So now I'd like to switch over and do a quick demo of the operating system. So I'm going to rotate my screen a little bit. I'm going to stop sharing so that everyone can see my video. This is the currently operating box just next to the Spinsolve. Currently, the solution is just pumping through the system. And then if I go on to our Spinsolve expert software and I hit run and acquire for here, I'm acquiring for just 13 seconds to get a quick RASER. And we see our RASER effects. We're shifted a little bit off here just because I've been acquiring for a long time. I need to shift the frequency a little bit back, and the shims are off, but the shimming does become an issue over a large amount of time. But again, we can acquire for maximum time. There I just acquired for used a 90-degree pulse for initialization, and then I'll change that to a 3.3-degree pulse and acquire again. And again, you can see very clear RASER right here. And at that, I will, I think, leave it to Boyd. If you want to lead up the question and answer period, I'll open that up so people can ask questions about the demo and anything that I showed in my slides.
All right, fantastic. That's a first for me, seeing a live demo in an actual talk at a conference, I think. Yes, we do have some questions. Sorry, there we go. It's also the first time I was hosting a talk from a person who had the power to take away all of my powers as the host, and I had to wait to get them back. Okay, so now I can do it. Let's see. All right, so the first three questions are very similar, so I'm going to try to combine them. Can you comment on the current and perhaps ultimate limits of your setup in terms of the fluid flow rate, the parahydrogen pressure, and the temperature?
Yeah, so current limitations of the setup in terms of pressure is 100 PSI. But the only limitation of that is actually the glass flow cell. So we're talking to Wilmad to try and get a flow cell manufactured that will allow us to go up to 200, 300 PSI. There is no, the Teflon itself can tolerate up to 50 bar. So we really don't see any limitations there. It's only, and the pump as well goes up to 2000 PSI. So the main limitation is the glass itself. And then you said flow rate.
Yep.
Flow rate, right now we can go as low as we want, as We can go up to 10 milliliters per minute with the pump that's operating right behind me. But again, as we go to higher flow rates, I think the main issue that we're having is this line broadening. If we want to actually prepare solutions and not monitor them continuously in the Spinsolve, then we could increase the length of our reactor and move to higher flow rates. And then we could quickly produce a much larger volume of hyperpolarized solution in a longer reactor. We just wouldn't be able to monitor it directly. That would have to be pumped out separately into a flow cell or into some sort of NMR detection modality. Was there another?
Well, the follow-up is what is the volume of the sample that is being observed inside the magnet right now?
So the sensitive volume of the Spinsolve, I think, is about, I think we estimated it's about 100 microliters. So we're refreshing that pretty relatively rapidly. The order of seconds is how fast we're refreshing that sample. And that's why as we push closer to 6 milliliters per minute, we're nearing the 1 second refreshment rate on that sample. And as that sample isn't only, it's only in this sensitive volume for 1 second, and we really don't get it.
Okay, next. That T1 of pyridine seems low. I remember it being around 30 seconds at 7 Tesla when the sample is degassed. Is it just a magnetic field effect, or was the solution you measured it on containing oxygen?
So the solution that I measured the T1 of pyrazine on at 1.1 Tesla was degassed, degassed methanol, degassed, well, pyrazine's a solid. So, but yeah, it was a degassed sample, no oxygen.
All right, let's see.
We were also surprised that the pyrazine T1 was that low at 1.1 Tesla, but it explains the lower levels of polarization that we're observing.
What is the benefit of using a membrane reactor if the sample is transported to the magnet for detection? Why not just bubble into a reactor and have a continuous flow cycle of the polarized liquid into the magnet?
So we're using the membrane reactor because with the membrane, we get a lot higher surface area contact between the hydrogen and the solution. So with bubbles, the surface area between the gas liquid surface area is much lower than in the membrane reactor, really because of the length of that system. And of course, we need to do this with something long-lived or fully characterize the relaxation effect to show this, but what we project is that we're actually getting higher levels of polarization than we would get with bubbles.
Oh, okay. Well, plus, and I can add just from my grad school days, is that if you were trying to do this on a sample that might foam otherwise,
exactly.
without getting too specific.
If it might foam, and I think this surface area effect is something that's already observed in shake and drop versus bubbling experiments, where when you shake the tube, you increase the surface area significantly between the gas and liquid phases. Where with bubbling, you have a limited surface area due to really how large your bubbles or how small your bubbles.
Yeah. Let's see. Specific question: where do the side bands in your slide 29 come from?
So the side bands on the RASER spectrum. I guess I can share that screen again. Sorry. If I can just find those. Okay, so this. Oh. Oh,
29.
No. Yeah, no, it's lost control.
No. What's it doing?
Okay. Okay. So yeah, those side bands. Sorry, I can't pull it up. I'm having issues with the delay right now. But those side bands we think are due to flow artifacts because they're dependent on the flow rate. The splitting between the main peak is dependent on the flow rate. So we're not exactly sure where that is. We're still investigating what causes that, but it's somehow flow dependent.
Okay. Is it possible to incorporate magnetic shield in your PHIP-MARS setup to transfer polarization to 15N under continuous flow?
Absolutely. We are going to be doing that. I'll be doing that hopefully in a couple weeks. when our shielding arrives. So I'm getting some very small shielding that can fit within that 2x2x2 box so that I can keep the system compact, and I'll be putting the reactor inside that shielding.
Okay, just a couple more questions. One says, it's a comment and then a question. I think the RASER is really interesting, but I don't quite get the motivation beyond a demonstration of the physics. So is there an actual motivation or application in mind, or is it just fun? Not that there's anything wrong with that.
Yeah, so there are a lot of applications. I think I'll leave some of the RASER applications to the next talk. I think Stefan Appold is following up and he's going to give a really great talk about some of the underlying physics, and then he'll probably discuss some applications as well. One thing that I can speak to is that when we're able to achieve this continuous acquisition, once we solve our adjustment in the Fourier transform for the drift of the magnet over time, then we can Fourier transform the entire RASER spectrum, and we'll get line widths that are very, very narrow in the millihertz or microhertz regime. And so that's kind of the short application, but I'll leave the rest about how great the RASER is to the next talk.
Okay, and we're running over and we have too many more questions. I'm going to ask just one quickly, and then any other questions, please take to the Slack. So the last question I'll ask is, why is glass necessary, and could you make a bigger sample?
So why is glass necessary for the flow probe? Is that
wherever you have glass, why is it necessary?
The glass flow probe is just what we have right now. It's not necessary. I'm sure we could come up with some other material. I mean, as long as it's suitable for NMR detection. That's the only place we're using glass right now. And then the other question, the other part of that was.
Well, you could make a bigger sample then. Right.
Oh yeah, we can definitely increase our sample size. There's a reservoir in the system as well. If we increase that reservoir, or if we just add more tubing, then we can increase the sample size. It's very easy for us to get up to 10 milliliters. We could actually decrease it even more. I could go down to 5 or even 3 milliliters if desired.
All right, thank you very much, Patrick. That was awesome. That finishes this session. I know we're a little over in time. Sorry about that. So we're probably going to have a short coffee break now.
I'd just like to say very quickly, I want to acknowledge all of my group that I'm sharing right now, and of course my close collaborators in the chemical and biomedical engineering. Sorry, I had to squeeze that in.
Oh, no worries.